Hey everybody, this is Mrs. Hiltz, and in this lecture we are going to go over types of bonding. All right, so the whole goal is for you to be able to identify an ionic bond and a covalent bond and understand that these two compounds, these two types of bonds, are named differently because how they are formed. So, one thing that they have in common is that they are made up of elements, of course, but also that the whole goal is to obtain an octet or a complete outside shell of electrons. All atoms want this to feel satisfied, just like the noble gases. And atoms can do this by forming bonds. So, ionic bonds. This is a type of bond that is formed when electrons of a metal are transferred to an atom or to atoms of a nonmetal. So when ionic bonds are formed, ions have to be formed. So that was not a coincidence that ion is the root word of ionic. And ions are formed by when atoms form charges. So when electrons are transferred from a metal, so giving electrons away so that the metal can achieve its octet, and transferred to the nonmetal, so it's receiving electrons so it can achieve its octet, charges are formed and ionic bonds are formed. Covalent bonds, these are formed between two nonmetals, so only nonmetals. Metals cannot be part of covalent bonds, and electrons are shared in this process of creating the covalent bond. And ions are not formed for covalent bonds because there aren't any electrons being taken away, so no negative charges being taken away, no negative charges being added, so no charges for covalent bonds. The electrons are being shared. All right, so a visual to go with this. Here we have a group 1 metal because it has one valence electron, and we have a group 17 or 7A nonmetal because it has 7 valence electrons. And for each of these to be satisfied, the metal will give away one of its electrons, and the nonmetal will receive that electron. The metal now has a complete octet with its lower shell, and the nonmetal has a complete outside octet or complete valence shell of electrons, and we can see that here with all 8 dots. And because an electron was given away, so it lost a negative, and a negative was gained over here, the atoms themselves are charged. However, the compound is not charged. And we can check that by just doing a little math. If we have a positive one here and a negative one here, add those together, you get 0. So the net charge of ionic compounds will be 0, but the charges are just within the atom. And that's actually what's holding the atoms together, the charges. Just like how opposite ends of a battery attract and hold strong together. Ionic bonds are extremely similar with that, where we have a positive and negative being attracted, and they're held together by that attraction. For covalent bonds, our example here, we have the same nonmetal with 7 valence electrons and another nonmetal, 7 valence electrons. Each of these needs one more to be satisfied, so they are going to share the electrons that are circled. So each of them now will feel like it has 8 valence electrons and a complete outside shell, and it is satisfied. So no charges need to be written in there because nothing was lost or gained, or no electrons were lost or gained. All right, so most of the periodic table, as we can see, is made up of metals. So many compounds are ionic compounds. When we are trying to identify if something is an ionic or a covalent compound, we need to know where the general location of metals and nonmetals are on the periodic table. Otherwise, we're going to have a hard time deciding if it's ionic or covalent. So if you have any of these light blue elements in a formula, you know that you are going to have an ionic compound because a metal is present and it will have to lose electrons in order to become stable. The nonmetals, if you only have nonmetals or metalloids, you will be forming covalent bonds, okay, because their electrons are going to be shared. All right, looking closer at ionic compounds. So this example, we have sodium, which is a metal, and sodium needs to lose one electron. When it does, it gets a +1 charge. Chlorine is the exact opposite. It needs to gain one electron, and when it does, it becomes -1 charged. And those two together form sodium chloride, which is just table salt. And even though we call these ionic bonds, like I was saying earlier, it's really just an attraction between the positive and the negative charges, but it's really, really strong. And that positive and negative attraction between table salt or sodium chloride is going to stay strong and held together until something were to break it. So something like water. Water can come in between that bond and separate it, and this is when salt would dissolve in water. And that actually can be reversed. If you take out the water, evaporate it out, you'll be left with salt again. And that bond reforms because the barrier that was in between the electrostatic attraction has now been removed. Molecular compounds, this is just another name for saying covalent compounds, because molecular compounds just state that there are two of the same type of atoms. And since covalent bonds contain two nonmetals, we have two of the same types of atoms. So that's why molecular and covalent can be interchanged pretty easily. But electrons are shared between the nonmetals so that all of the atoms involved feel like they have a complete outside octet. So no transferring of electrons, no charges are being created here. All right, let's make some predictions. So I'd like you guys to pause the video and predict if you think that each of these compounds is either ionic or molecular. When you are ready for the answers, press play. All right, let's check your work. Okay, so the first one and the last one ended up being molecular or covalent compounds. That is because they contain only nonmetals. And we can check that by looking at the periodic table and seeing where they're located. They should, all of those atoms, nitrogen, oxygen, sulfur, and fluorine, they are all in the upper right-hand corner and are all nonmetals. Na2O, or sodium oxide. This is an ionic compound because sodium is a metal. Calcium chloride, CaCl2, this is also ionic because calcium is a metal. Right? And your metal will always be the first one in the formula. Okay, so the rules that go with naming these compounds, for example, the first one is nitrogen dinitrogen monoxide, meaning two nitrogens, one oxygen. This one is sulfur tetrafluoride, with tetra meaning four. And then these two, sodium oxide, calcium chloride. So notice that when I named the covalent / molecular compounds, these ones I added things like di meaning two, mono meaning one, tetra meaning four. That is because we need to be told, or that is the difference in these namings. We need to be told how many atoms we have of all of the atoms present in molecular compounds. Where ionic compounds, we don't need to state the number of atoms because we will use charges that are known to figure out what the formula is of the compound. Okay, so here's the rules for ionic. Metals will lose their electrons, and the goal is to achieve the electron configuration of the previous noble gas. When this occurs, they form positive ions or cations. Nonmetals tend to gain electrons with, again, the same idea of achieving the electron configuration of a noble gas. And when they do this, because they're adding electrons, adding negativity, they become anions. Okay, so overall goal, S2P6 electron configuration. All right, so with electron configuration and bonding, the bonding occurs between the valence electrons because those are the electrons in the outermost energy level. Okay, and those are also the electrons that are gained and lost, gained, lost, or shared, depending on the type of bond that is being held. And the electron configuration of the atom, this can give you an indication of how many electrons will be gained or lost to get to the noble gas configuration, just by looking at those exponents of, flip back a slide, the S2P6. We need a total of 8. So if we have S2P5, we know that we need one more. Or S1, we know that we would need to give away one. Then we get that configuration from the previous period or previous noble gas. All right, here are the charges of the different groups, all based on how many electrons they need to give away and how many electrons that they need to receive to achieve that noble gas configuration. All right, so how you write ionic formulas from their charges. Here are the steps. You first need to identify the name of the metal, or the metal and the nonmetal. So when you do this, look up to see what its charge is and what the chemical symbol is. The charge of the cation will be based on the group number, and the charge of the anion will also be based on the group number. You'll use the charges of each ion to determine how many of each you need to make a neutral compound. Then you'll write the formula by using the chemical symbols and using subscripts to adjust the number of atoms. So, for example, we have sodium and sulfur. So what we are going to do is first look up sodium on the periodic table, and we would see that its chemical symbol is Na, and because it's in group 1, it has a positive 1 charge. Then our nonmetal is sulfur. We would look up and see that its chemical symbol is S, and its charge is -2. Also, I knew that this was a metal because sodium is in group 1, so it's on the far left side of the periodic table where the metals are located. And sulfur is in the upper right-hand corner where the nonmetals are located. So that was my first indication that this was an ionic bond because I have a metal and a nonmetal. Then I'll use the charges to balance this out. Because sodium's +1, I'm going to need 2 sodiums to balance out that -2 charge. So my formula is Na2S. Okay, and again, the sum of the ionic charges is always equal to 0. All right, we got some more examples. If you're feeling confident and want to try these out on your own, go ahead and pause the video, follow the same steps of finding the charges and balancing it out to determine the formula. When you're ready for the answers, press play. All right, let's see how you guys did. So lithium has a positive 1 charge. It is a group 1 metal. Nitrogen is a nonmetal. It's in the upper right-hand corner and has a -3 charge. We need 3 lithiums to balance out nitrogen's -3. So we have Li3N. Second one, barium is in group 2, so it is definitely a metal, and it has a positive 2 charge because of that. Chlorine is in the upper right-hand corner and is a nonmetal. It's in group 17 or 7A, so it's one away from becoming a noble gas and has a -1 charge. Because barium has a +2, we are going to need 2 chlorine atoms at a -1 charge to balance that out. So our formula is BaCl2. All right, why don't you guys give these a try? So given these atoms with their charges, I want you to determine what the formula would be after those charges are balanced out so that the ionic compound has a net charge of 0. When you're ready for the answers, press play. All right, let's see how you guys did. All right, Li2O, 2 lithiums at +1 to balance out the -2. We need 3 chlorines to balance out the +3 aluminum. And for this last one, we need 3 magnesiums and 2 nitrogens, so common factor of 6, to balance those out. And we have a little trick here that I'll show you guys. The charge of the cation, just the number, not the actual plus or minus, ends up being the number of atoms of the anion, and vice versa. So since we had 1 here and 2 here, we had 2 and 1 atoms. Then for this one, we had 3 and then 1, 3, 1. Last one, we had 2, and then 2 of the other atom, 3, 3 of the other. So just a little short trick. All right, now there are metals that have different charges, so that's what we're going to talk about next. And these are the metals in the D block, or the transition metals. These ones can lose s electrons from their higher energy levels, as well as d electrons. And because of this, they can form 2 or more positively charged ions. So you could have a +1 charge, +2 charge, all the way up to +7. And because there are varying charges, we need to tell the reader or the scientist or the student what metal, specifically what charged metal, we are using. There are some exceptions to this. For example, zinc, that has a +2 charge and it is a transition metal. That's the only charge it has. Same thing with silver, only 1 positive charge, even though they do live in the D block or transition metal group. Here's a list of some common cations that have multiple charges. And when we are writing the names of these, this is actually how it is going to look, where you have to state the charge for chromium +2 or +3, just to state which chromium ion we have, or that we would need to use in our formula. All right, and here's some more examples. If we have iron +2, it'd be written iron 2, iron 3, like this, copper, copper 1. And again, this is the charge written in parentheses. Sometimes students get confused and think it's the number of atoms present in the compound. It is not. It is always going to be the charge written in parentheses following a metal. All right, we got some examples. So if you would like to try and name these, you're welcome to do it. But I'm going to go over the answers in 3, 2, 1. All right, so I showed all of the work for how I found the charges of all of these transition metals. And in general, I use this formula where you take the charge of the metal, which we don't know, so that would be our variable, the number of transition metal atoms, which is given to us in the formula, add it to the charge of the anion, which that we can find by looking it up on the periodic table, and multiplying it by the number of anion atoms. Add those two groups together, and you need to equal 0. So we end up with gold 1 sulfide, iridium 6 fluoride, tungsten 4 sulfide, titanium 4 nitride, and vanadium 5 fluoride. All right, if you want to check out the work for how I solved each of those, please pause the video, and when you're ready for more, press play. Okay, so to wrap it up, what you guys need to know about ionic and covalent naming is just how and why they have different types of naming. So ionic formulas, again, these are based on the charges of the cation and anion, so based on the charges of the ions that make up the ionic compounds. And because the charge of the ions are defined, so we know these charges, either they are obvious to us, especially for group 1 and group 2 atoms, because +1 and +2, or we can easily figure them out with the transition metals, but they are known and defined charges. We use those ratios we use the ratio of those atoms to come up with a neutral compound. And the naming, cation, anion, change the ending to IDE. And only if needed, you'll write the charge of the cation in parentheses. For covalent, covalent formulas are a result of sharing electrons. So ions are not formed, charges are not formed. An octet is still achieved, however, by sharing those electrons. And since there is not a fixed ratio that is always appropriate, because atoms can share more electrons if they'd like to, there's not a fixed charge for all of these. we need to indicate how many atoms there are of each present in a covalent compound. And how we do that is by using the prefixes in this table. So you'd write prefix, name of first element, then the prefix, name of second element. The ending is still changed to IDE, so that part is consistent with ionic naming. And some examples to end. So covalent, if we were given this compound, it would be nitrogen dioxide, di meaning two, and H2O, instead of just water, it's actually dihydrogen monoxide. Again, di meaning two, mono meaning one. This is one weird part about covalent naming. You do not use the mono prefix on the first element. The only time you'll use the mono prefix is on the second element. But you will always identify the number of atoms of the first element as long as it is 2 or greater. And last one, if you were given the name, you need to write the formula. Dinitrogen monoxide, 2 nitrogens, 1 oxygen, so N2O. Ionic is not as straightforward with telling the number of atoms of each because we use the charge to figure out the name and the formula. So if we were given KCl, we would see that potassium is a cation or metal. It has a positive 1 charge because it's in group 1, and knowing that it is in group 1 is really all we need, because then that tells us we do not need to use Roman numerals to indicate the charge. It's known. So the name of this is potassium chloride. Or if we were given FeBr2, we'd see that iron is a transition metal, so it's an ionic compound, and it's in the D block. Iron can have more than 1 positive charge because of its location. So possible charges of iron would either be +2 or +3. We can figure out which one it is by using our formula. So bromine, the anion, it has a negative charge of 1. Since we have 2 bromine ions and only 1 iron to balance it out, that iron has to be positive 2. I have a little diagram drawn out down here. So if we were to draw out the atoms, 2 negatives, that big one has to be a positive 2. So our name would be iron 2 bromide. All right, let me know if you guys have any questions. Thanks for watching.